Hello and welcome to Weapons of Math Instruction. This is our fifth and final video in celebration of Pi Day 2022, which was back on March 14th. Once again, I meant to get this video out last week, but I ended up traveling at the end of the week and I couldn't get it done, so I'm dropping it on you today. So in this video, I'm going to present a proof that pi is irrational that was given by Nicolas Bourbaki. In the last video, I presented Ivan Niven's proof that pi is irrational. Like Niven's proof, Bourbaki's proof is a proof by contradiction. So, let a and b be natural numbers, and let n be a non-negative integer. So, like I said in the intro, this is a proof by contradiction. Just like in Niven's proof, we're going to assume that pi is a rational number. So in this proof, we are going to define this function a sub n of b, which is defined by an integral. And those of you who watched the last video will recognize this polynomial of degree 2n right here, because that's just little f of x from Niven's proof. So, I don't want to have to prove this all over again. So recall from Niven's proof that all the derivatives of little f at 0 and at pi are integers. We proved those two lemmas in the last video. And that's under the assumption that pi is rational. So when I get to the part of the proof that invokes the integer valuedness of these derivatives, that's where the assumption right here comes into play. And again, we're deriving a contradiction from that assumption. So what we're going to do is expand this function a with repeated integration by parts. And there's going to be a lot of writing in this process. So I'm going to define this function g of x, which is b to the n times f of x, just so I don't have to keep writing this b to the n over and over again. So let's just take a note of something here. Since g of x is this integer, b to the n, times f of x, and since all the derivatives of f at 0 and pi are integers, all the derivatives of g at 0 and pi are integers too. And again, I can't stress this enough, that's under the assumption that pi is rational. So here I've written the function a in terms of g of x. And off to the side I've written the parts that we'll use. And here I've applied the integration by parts formula. We'll do this a couple more times. Here's the next set of parts. And the next iteration. One more set of parts. And one more iteration. And notice that a pattern is developing. Even ordered derivatives of g are paired with cosines, like here and here. And odd ordered derivatives of g are paired with sines, like here. Extending this pattern until the last bracket contains the 2nth derivative of g, we get this expression here. And this plus or minus sign is there because the sign of the last bracket could be positive or negative, depending on whether n is even or odd. Now, as we noted on the last slide, all the derivatives of g, and of course g itself, are integer valued at 0 and pi. And of course sine and cosine are integer valued at 0 and pi. So all of these brackets are integer valued, and so their sum is as well. Also recall that g of x is a polynomial function of degree 2n. So the 2n plus first derivative of g is 0. It's the 0 polynomial. And so this integral is 0 because the integrand is identically 0. From this we conclude that a sub n of b is necessarily an integer. At the endpoints of the interval of integration, 0 and pi, the integrand is equal to 0. And on the open interval from 0 to pi, which is the interior of the interval of integration, the integrand is strictly positive. So the integral of this thing, which is equal to a sub n of b, is strictly positive. Also, this inequality holds. How do I know that? Well, here's how. If you graph y equals x times pi minus x, you get this concave downward parabola, whose vertex is at pi over 2, pi squared over 4. And so, consequently, all the values of this expression here are less than or equal to pi squared over 4. Now, what we're going to do next is build up the integrand in the middle member of this inequality so that we can put bounds on it. So here, I've raised all three members of the inequality to the nth power. And here, I've multiplied by b to the n over n factorial. And to finish building the integrand, I've multiplied the middle member by the sine of x. Remember, on the interval from 0 to pi, the sine of x is between 0 and 1. So I can multiply the middle member by the sine of x without changing the bounds. So this gives me bounds on the integrand, and now I can place bounds on the integral, which I've done here. On the right, we have an upper bound for this integral, which is equal to the upper bound of the integrand times pi, which is the width of the interval of integration. And here I've just rewritten the inequality with a sub n of b in place of the integral. Now remember, n is arbitrary, which means it can be arbitrarily large. So as n grows arbitrarily large, the upper bound on the integral grows arbitrarily small. Why is that? Because this n factorial grows much faster than this exponential. But since a is positive and integer valued, this is a contradiction, because there is no arbitrarily small positive integer. The smallest positive integer is 1. Therefore, our assumption that pi is rational must be wrong. Therefore, pi is irrational. And this completes the proof. Thanks for tuning in, and I'll talk to you again soon. Hey everybody, if you enjoyed this video and want to see more like it, then please do follow me on my socials. You know you want to.